Good afternoon, everyone. My little Tuesday tidbit this week, observation that birds likely do far more people watching than we do bird watching. So as we get started here, wanted to just briefly mention something that we started publicizing last week. In 2018, ResFrac led a joint industry study on DFIT analysis. We took a 2-year break at that study, but we are preparing and launching another study for 2021 that will extend for 15 months on studying parent-child interactions. We really view this as an existential issue for the industry. We have a uniquely capable solution, the entire life cycle and child wells and parent wells all together. And so we want to use that to investigate these various parent-child interactions that are unique by basin. It looks like there is marked differences in the heuristic scene in the Bakken versus the Permian versus the Haynesville. And so by bringing together many of these data sets from across the various basins, we think it'll provide very unique insights and be able to bookend and compare the various mechanisms that we propose to explain the interaction that we see between these wells. So if you have more interest, email myself or Dave or Mark, and happy to have a conversation with you. Getting going, we'll go quite quickly through the ResFrac overview for those that ResFrac is new to. Our objective as a company is to maximize the economic returns. We do so in an unconventional environment by looking at sensitivities on completion design, whether that is cluster and stage spacing, or EOR, IOR potential, or parent-child interactions, as we just said in the last slide. And our unique capability of answering those questions revolves around the ability of the software to simulate fracturing, leak-off, closure, production, refracs, child wells, EOR, all in a single simulation model. And so on the next slide, I separate that into 3 dominant processes that I think of. So the first would be hydraulic fracture propagation and tracking of proppants and fluids where those end up. We then, of course, have to produce into those fractures, which is the reservoir mechanisms of multi-phase flow. And then finally, we have a geomechanical impact from that pressure depletion. And all of that is being calculated in one code. The next slide has a quick demonstration video of all those processes being coupled together. So if we play this is a parent-child simulation. So 2 parent wells are going to be fracked here and then produce for a little over 4 years, I think. So there's my 2 parent wells. I'm then producing, we can see that pressure depletion, and now infilling and fracking 3 child wells. And then we can see all wells deplete together. So all of that is being coupled and solved in a single code, which adds realism as well as simplicity to the workflow. But as Dave is going to cover today, also means that we have many more heuristics and observations to match. And so we want to go through in a logical order when history matching these complex simulations. So as a company, we both license software. We also do consulting. Today, we'll focus on technical content, but as always, feel free to contact me afterwards with questions on commercial engagements. And here we go. Dave is going to speak today about history matching. Dave's going to draw upon a wealth of experience we've gained across these various basins. Don't know whether or not he's allowed to say the basin in which the data set's coming from today, but we do our experience rather spans from the Montney in Canada all the way down to Vaca Muerta in Argentina. With that, Dave, I will turn over to you.
All right, guys. Today I want to go over the perils of the non-unique solution. So basically a gut check. When Bob Barker, tribute to, by the way, Brian Gilmore and Bad Movies. And we'll up the ante one more on this one, as I've seen this movie on several occasions and not just one occasion, which is more sad than the Will Ferrell movie, I think.
That's the best movie ever made, Dave. That's Happy Gilmore. Come on.
Are you saying that Happy Gilmore was a bad movie, Dave?
Well, all right. I've seen it more than I should have, and along with the water boy, I've seen it more than I should have. But
I feel like that
what
was
we
a
can deduce out of
definition
this,
entire
Two best,
generation.
two best movies most underrated for an Oscar, right there. Waterboy and Happy Gilmore.
well, what we can deduce out of this is that Bob Barker hates the Boston Bruins, which, you know, that should just go without saying. But no, I mean, it's anything, you know, when we have the ability to have non-unique solutions, you have the ability to create very, very large mistakes. And you think of old Bob there as the stockholders once you try to pass those mistakes off as a well spacing or something like that. So let's get into it. My main goal here is not so much delivering a super technical content like Mark would. It's just, what are those parameters and what kind of range should we be looking at, and what's going to give me that warm fuzzy feeling at the end of the day that lets me know that I'm pretty doggone close to a history match. So what I'm showing here is two different cases. On the left, you see a case that you know which one is more correct. You know, you got one on the left there, you got one on the right. The one on the right doesn't even look close, but the one on the left, boy, it's not bad, but there's sure some problems that we could see with it. So let's look into that, case number one. So initial observations. Well, you know, if we look in the bottom right-hand corner, the RTA slopes, you know, we even got a little y-intercept that's matching that initial y-intercept. We've got those look pretty decently matched. The cumes, rates, cumes, etc. Those are, you know, they're okay, they're matched. What we do start seeing is that our initial GOR is off. So definitely something is wrong here. So whatever I had to do to match this, I really screwed up over here. It's also not moving upward. So the GOR trend is not moving upward. We don't see this. The water cut's really high. So that's not generally really good. Another thing to notice though is if you look at the rate here, really, really flat. So that's something interesting to observe. And you know, it's not saying that that's wrong. It's just something to look at. Obviously, something happened here that caused an increase in the gas rate. You can see a very small inflection there, but if you look over here, that rate is actually pretty well honored. So something is happening here that is not happening here that allows us to see that little increase in the gas rate and even a little bit more in the water and the oil rate. So something's happening. And I'd like to point out that, you know, we got a little bit of initial flow back here, but the drawdown is pretty consistent. So let's look at this. What are some red flags that once I've gone through the simulation, what are some of these red flags that kind of pop out at me and go, hey, you know what, this can't be right. The first one I noticed looking through it was the improper embedment. And I don't remember what the actual default in ResFrac. I think the default in ResFrac is 0, actually, so no proppant embedment. But I actually had 0.2 pounds per foot for 100 mesh, which is actually 2.5 times the proppant diameter. So this was a carry through. In this instance, we had history matched other wells that had 30, 50 mesh. And so this is kind of carried through from there. And I forgot it was there. So when you go to 100 mesh, you need to change that proppant embedment because it's, you know, a lot smaller proppant. One of the things I had done on this was I was really looking hard at this fracture conductivity with this y-intercept here on the RTA plot. And I had lowered it and lowered it and lowered it. And I finally got my fracture conductivity to, you know, it kind of matches that slope as we're seeing here. But as I matched it, I had to do other things. And it's a little hard to quantify just by looking at it, but this is actually much lower than anything I've run before. And you'll notice that because of this, the character of the rates are nearly non-existent. And I began to deduce that I had a problem is because after running multiple simulations, I was noting that, you know, I would change a parameter and they weren't really having much effect on the outcome. And basically I started to deduce, well, you know what? The formation isn't controlling production. The fracture is controlling the production. The fracture, the rail perms within the fracture were actually controlling the production more than the actual formation. So I knew I had something going on wrong. Proppant immobilization, I kept trying to increase my proppant immobilization to decrease the area to match this little GOR trend, even though I didn't have my proper initial GOR match, which is the very first thing you should do. You should be matching your initial GOR, and I'm not doing that. Water cut, no matter what I did, I couldn't change water cut. That's kind of harkens back to that the fractures controlling production versus the formation. Leak off and closure. So if you look, you should always be looking to see how long it takes for your fractures to close. In the UI, there's a parameter called E open. And that just basically, it gives you the open part of the fracture, or the part of the fracture that's not touching the proppant or the other fracture walls if there isn't any proppant. And the closure on this fracture in this area, I knew should have taken about, let's say 24 to 30 hours. It was happening in, 30 minutes or so. So I knew there was something wrong there. Had to fix that. And then finally, in order to match this initial y-intercept here, I kept having to increase the perm, and that was due to the conductivity, the fracture being so low. And pretty soon I found myself, well, heck, I got a 6,000 nanodarcy permeability and a formation known to be approximately 40 to nanodarcies. That doesn't make any sense. What's going on here? I can pretty much say that this is a non-unique, not very good solution. So what do we do? Well, let's just start, kind of do some course corrections here. Let's start from the beginning. Let's just take a step back and let's see what we have here. So the first thing I did is I started to understand that fracture conductivity was having a big effect on the simulation. I increased it until basically I did not see a change in production. So I kept increasing that fracture conductivity until I could be pretty confident that it wasn't the fracture controlling the production, but rather the formation. I just reset the proppant immobilization to 0.5 pounds per foot squared. We'll see where that lands, at the end of the day. But it was obvious that when I was doing that increasing proppant immobilization, that it wasn't having any effect anyway. So I just reset it back to another number. I decreased the proppant embedment to 0.04125, which is, if you do the math, and you can see that in the builder, if you ever go and want to know how proppant embedment is set. I set it to 50% of the proppant diameter of 100 mesh. The cool thing about changing your proppant embedment is that you can double your fracture conductivity, but if your fracture conductivity in the prop section is already really, really, really low, doubling it's not going to make much of a difference. This is kind of like a step change over the entire fracture because you're literally lifting the proppant up and out of the matrix. So you kind of get just kind of a blanket increase, a constant increase over the entire fracture. I just took a number. I said, well, this formation should be about 80 nanodarcies, give or take, which, it's a 75x reduction. But I said, it's got to be in this range. So what do I got to do to get there? I adjusted PDP, the initial pressure. I did that to promote faster closing times due to that reduced permeability we're seeing. Left rail perms alone until I get a little bit better understanding of the production. And then I increased the bubble point to match the initial GOR rates. So basically, if you just look at your fluid model, and this is a very complicated fluid model we have in here, but if you look at the fluid model and the rate at different pressures, you should be able to figure out what your actual bubble point is. And we didn't have a great handle on that. So what does it look like when we're done? So here are the final results. You can see now we have the rates and the bottom hole pressure are matched pretty well. Cumes are matched. We are not getting the in the RTA analysis, we're not seeing the y-intercept like we saw before. And now that I look at it, and I've been doing it, had the history of trying to match the y-intercept here, I can say to myself, well, you know what? Maybe this well was kind of cleaning up on its own, or something was happening. It almost looks like we have 3 separate slopes here, and maybe this is the y-intercept I should have been matching this entire time, which if you bring that down, goes right down to the origin. GOR is actually looking really good now. We got that nice little upward bend, and the water cut is looking well as well. And I'm not going to tell you the final numbers that I matched to, but I can tell you that it is actually really, really, really close to where I had here. And just a slight reduction in perm. Proppant embedment was left alone. Proppant immobilization was left alone. So I was way closer than I thought when I started the project versus where I ended up. So And those are those gut checks. Those are what you need to understand that, something else has to be going on, because I can't just sit here and say permeability is 6,000 nanodarcies when I know better. So from here on out, I just want to kind of give, this is, match your areas first. And then here are the kind of the range of parameters to start with. I mean, all it is just kind of giving a starting point. Could these parameters, could you match something with a parameter out of this range and still be correct? Yes. I'm not saying that this is a tried and true fast numbers. This is just starting points. And because we don't know what these numbers are. So start out with your frac lengths and your proppant cloud. Ballpark using proppant conductivity measurements, pressure interference tests, fiber optic measurements, offset well frac hits, microseismic, GOR curve shape, etc. Just ballpark it, get it close. And then, the one thing I've been noticing is that the frac lengths are probably longer than you think. So if you've got 300-foot frac lengths, I'd be wary unless you put on a really, really, really tiny frac. So some ballpark numbers. Start out with your proppant immobilization maximum at 0.5 pounds per foot squared. Your immobilization rate, start out with the default, which is 0.1. That might be minute to the -1. Can't remember. I might have got that wrong, but just 0.1 is the number that you want. If you need, you can change that rate. And if you need for that proppant cloud to be smaller, you can increase the rate and increase your proppant immobilization, or vice versa. And that will, get you that proppant cloud that you need, whether it's 200 to 500 foot proppant half lengths. And we know permeability should be about 10 to 100 nanodarcies in most shales-ish. I mean, take it with a grain of salt, but that's about where you should be at. The pressure-dependent permeability, the pressure, is going to be dictated by SH-min and pore pressure, so it's a little hard to give you a range there. The lower the difference between SH-min and pore pressure, the harder it is to get your formations to leak off. So, consider that your SH-min calibration or the SH-min you got from the service companies may not be quite right, and or your pore pressure may not be quite right if you just absolutely cannot leak off the fractures. And usually that multiplier should be somewhere between 1 and 50x. And honestly, I'd say it's probably lower than 50x. Toughness ranges somewhere between 750 and 2,500, with probably 1,000 to 1,500 being even a tighter range. And then we have that parameter in ResFrac called relative fracture toughness. And that is a toughness scalar based on the distance that the fracture travels, either height or length, you can set it. But usually it's going to be around 0.05 to 0.3. And if you're using very much higher fracture toughnesses, it's possible you just might have a lower toughness. But different combinations of these things can work. But I'm just saying this is probably a good starting point. So let's look at fracture conductivity. Very important to not take a well and try to history match it, which might have problems. Especially if you think this well is not producing to its capabilities, then, we don't want to try to history match that, because we might use permeability to history match that lower rate, and therefore, decide that our well spacing is a lot smaller than it is. Use a good well. Use a well that you're really confident in the production. We want to ballpark that total production at first so that we can make sure that our fractures can handle the production. Just make sure that it's close enough. You're getting the deliverability you want without being constrained by a fracture. The proppant K0, so this is that number I've been telling you about, fracture conductivity, proppant conductivity, however you want to talk about it. The conductivity tables are supplied by the proppant supplier, and there's an input into the wizard. Start out with that. In that table, there is at the very bottom of that table, when you enter it in, you can actually apply a multiplier. Start out with about 0.3. So it's going to take the conductivity that is going to be calculated from the tables that the proppant suppliers and just multiply it by 0.3. So it's going to reduce the conductivity by that much. I'm not saying the proppant suppliers are over-promising their proppant, but this is what will get you kind of in the ballpark. And then, like I said before, increase K0 until you see little change in the production. and then back it down until you don't see that change anymore. We don't want the fracture to be, at least right now, what's causing problems with the production. We want to get that permeability in the matrix correct. And then these are the proppant embedment recommendations. This increases the conductivity over the entire propped area by set amount versus just doing a multiplier. That will actually help draw down a larger area, which will flatten out your GOR curve. So you can use the GOR curve to help tune this. And the more conductivity, the more proppant embedment you have, the higher likelihood that your GOR curve will bend upward faster. 50% is probably pretty good. If you're using something different besides one of these three, then do the calculations. And then finally, as far as the production part of it, permeability. It's a big part of what drives everything. So don't forget that your permeability is equal to that static model perm, that perm that you entered into the static model, times any global permeability multipliers that you might have used, multiplied again by that pressure dependent perm if you're in that pressure regime. So just make sure you're taking account into everything. And then of course you have your relative permeabilities as well. I don't have as much guidance on that because you're just going to have to match your production. All formations are different. But I will say that if you are using relative perms to match production and you notice that your curves are becoming lower and lower and lower, meaning that everything is below 0.1, then consider increasing your perm, decreasing your permeability, and then increasing the rel perm by the same amount so that you can get some more character in your rel perms. So this, like I said, this is gonna be a little bit shorter, but basically just wanted to give the gut check just to make sure that we're in the right ballpark with everything, because if we had used 6,000 nanodarcies for well spacing, there would have been some angry investors, I guarantee it. So the goal is to arrive at a matrix permeability that reflects the actual permeability. If the simulation is fracture constricted, then it can be very, very difficult to get that correct permeability. Future optimization runs need to reflect the deliverability of the matrix and not necessarily the deliverability of the fracture. We're going to assume that very low permeability formations, that the fractures are able to deliver the necessary flow. We don't need a fracture superhighway, but we need to be able to recognize when those fractures are constricted at the same time. So it is, there's a bit of a tightrope sometimes. The optimized production will then reflect any potential gains from an optimized design. All right, so by the way, once you have gone through and you have done you got your right surface area, you've made your changes to your permeability, your PDP, etc., toughness maybe, don't forget to every so often go back, rerun the simulation from the beginning without a restart, if you're using restarts, to ensure that the changes on your history match did not seriously affect your changes in fracture geometry. And with that said, that is what I had. If you have any questions, I get these emails right here.
Pick one off from the chat window as folks get their own questions formulated. So this one was a little ways back asking, I think here on process.
So in this instance, there was conflicting permeability estimates. And then there was a very low defit perms, and there was very, very, very high defit perms. And we were just kind of going back and forth, trying to figure out what the best way was. The fact of the matter is, I actually started out with the right perm and went really, really high up because there was a question of what it would take to get a match with the higher perm. So it was kind of a, we knew better, but did it anyway just to see. That makes sense. So this question is from Tiffany. She says, could you explain more on how changing proppant immobilization rate affects GOR? Okay, so proppant immobilization, you're talking about the rate, Tiffany? Or are you talking about the You're talking about this one right here, right? I'm going to assume that's it. So as you increase the proppant immobilization rate, you will hit this proppant immobilization maximum faster. Okay, so if you were to increase this to like 0.4, then you would, very quickly increase this, reach the maximums on the proppant immobilization. That's the total amount of mobilized proppant per foot squared. And you would probably effectively reduce your propped surface area, and therefore you would increase your GOR trends would probably increase quicker. The same goes
maybe to elaborate on that point a little bit. There's this balance always on what's the conductivity of the fracture and how does that then impact the transmission of bottom hole pressure into fracture pressure. So in a infinite conductivity system, the propped area of the fracture would be drawn down to the same pressure as your bottom hole pressure, right? And so that is the scenario in which you have the highest GOR in an oil well. If you have finite conductivity, then there's some pressure differential between the propped region of the fracture and the well bore. And so one way to achieve infinite conductivity would be to have more proppant in and around the well bore, which increases the conductivity of that near well fracture area. And so that's where Dave is saying with increased immobilization rates, generally the length of the fracture would be curtailed and you end up with more conductivity next to the well bore.
Right.
Now, you could also, if you had super conductive proppant, maybe you don't need that much next to the well bore. And that's what that K0 factor does in the proppants table, right? And so it is a bit of a yin and yang to figure out, what's realistic. And also worth saying, once you reach that infinite conductivity threshold, increasing immobilization beyond that point won't yield further increases in GOR. Right, so once you've eliminated the delta P between the well bore and the fracture, that's the point at which you're going to reach your maximum GOR, and it's not going to continue increasing beyond that point, at least not in a meaningful manner.
So, quick question, Dave and Garrett. I was confused with what actually K0 is. So I can see a K0 in ResFrac in the proppant, basically section, but there is a K0 that doesn't have any unit, and there is a maximum embedment immobilization, which has the pounds per square feet. So which one is this? Because I see different proppant can have different basically.
That is correct. Yeah, K0 is in the proppant conductivity table that's there. It's actually calculated. You can calculate it from the wizard, or you can just start with a number if you know what your proppant conductivity is. And then the proppant embedment is specified on a layer by layer basis in the static model. It's the very, very last column in the static model. Mm-hmm. And the original intent on the embedment, by the way, is I was simulating the ash beds in the Powder River basin, and it was very apparent that the proppant was probably getting past those ash beds, but was probably being embedded to the point where the fracture had closed. So we used a very high embedment in that region. So that's why it's there. Plus, it ought to be, I suppose.
Thanks a lot.
Yeah. So the immobilization and embedment are both physical parameters, and K0 is just a multiplier to the fracture conductivity.
Right.
Or the proppant conductivity, rather.
Okay. Thanks for the explanation.
All right. Well, like I said, if you have any questions, we answer both these as quickly as possible. So feel free to ask questions. So send me an email if you have any questions, or if you have problems with the simulation, I can definitely help you out with that. As always, the technical write-up is available. There's also videos online. There's a lot of different ways to get information. Also, I think the most helpful thing that's happened, since 2 years ago when I first started using ResFrac, is all the little help buttons on the side. And they got a detailed explanation of what's going on. They usually have the equation there. It's like proppant embedment. That's an easy one, but you can go through and calculate however much proppant embedment you need, maybe based on any kind of core studies that you've done. So, like I said, nothing is black box. So that's very, very helpful, and we're willing to help whenever you can't figure it out on your own. Different literature, different SPE papers, and then finally, Garrett keeps saying that I got cut off. I killed my computer. I got the blue screen of death when I tried to switch over and show the snowstorm we're having. It's now 85 degrees outside, but my neighbor has a wildlife cams, and I thought I'd show the wildlife cams as well. Oh, I forgot about this, the joint industry study. Garrett's already mentioned that. If you want to stay around and look at
that's a backup slide, you can skip that one.
Oh, okay. Here is my next cross the street neighbor. That is a cougar. Oh. Sucker was, just right across the street. He's actually heading to my house, if that makes me feel any better. I don't. Then the other day, this happened 2 days ago on his back doorstep.
Does your neighbor dribble meat juice around the outside of his house each night?
I don't know. It just makes me want. I know why my dogs get up every night though. There's usually three possibilities. One, there's deer. Two, maybe a bear or mountain lions making some noise. And three, and what happens the most often is there is a skunk out there, and they go out and they get sprayed. They've been sprayed about 4 or 5 times now. Yeah, somebody said, yeah, he's looking for the doorbell. He wants in. I think that's his kitchen right here too. So he's probably smelling something, and it's like, hey, let me in. It's time for dinner. And we did a bike race up in the hills a few weeks ago, and several of the bike racers got stopped by a bear that was in the middle of the trail. Actually reared up on them, and they just sat there and said, you know what? Winning a race isn't worth it. So they sat there for 5 or 10 minutes. Anyway, let me know if you have any questions. And thank you very much for joining us this afternoon. I appreciate it.
And look forward to chatting with everyone in 2 weeks.